So. We'll keep working with the same data sets as I have been today, or use the same do files. We should kind of finish review of statistics. After class, I have one more section of 371. I'll get up the practice problems for the first quiz. So that first quiz I'll have kind of released after I get back to my office today around 1 o'clock. And the practice problems will look very similar to the kinds of questions that you'll see in that. You'll have until we meet in class on Tuesday to get that quiz done. So once again, the quizzes will be about every 2 weeks. It's open book, right? Have your notes open as you're working on it. They're meant to be questions that kind of get you prepared more for the midterm, some kind of lower cost, because you can have, your materials with you, you can have resources in front of you. So you'll see that pop up as well as that practice exam. Also, the first assignment. So let me see. I should have it still here. We'll see the first assignment up there. I think I've got it. There. So this will be it's got a bunch of different questions. You're meant to use Stata to answer all this. I'm going to have this data set sitting there. It's or that'll keep kind of posted with it. It's like a GPA data set. So kind of use that. And we'll do some work in Stata today. We don't have to worry about any of this importing. You can just open up. It's kind of Stata data file. So I showed you that once we do import Excel documents, things like that, we can save it as a Stata file. So it's just easier to just kind of from the interface open it up later on. I'm giving you the Stata file, so you don't have to worry about importing anything. You'll then kind of go through, use Stata to answer all of these different questions. You'll notice in some of them, we'll talk about this a little bit today, like are these statistically, is this difference statistically significant? Once again, this will make a little more sense after today's class, but you might have to write out a response. So a lot of people, if I've said this before, I'm probably being a broken record, but I'm just making sure we're all on the same page. You can just do all of your code in that do file and then put kind of comments in to answer these different questions. Now, what helps me out is if you put in your do file something like, you've got a bunch of code, then maybe you say you're answering question 2. Yes, it is, blah, blah, blah. So if there is some type of response you have to give, you can do it all in your do file using comments. It's helpful to me if you kind of label what question the comment is going to. And then also, if it's easier for you and you want to do that stuff instead of doing comments in the do file, you can have all of your code and submit that do file, and then you can put all of your responses in a Word document. I kind of have usually it's like a mix half and half. Half people will choose to kind of submit this Word document. The other half can do all of their work in the do file and just upload one file. Okay. So you just have one data set to use for that problem set. It's I'll give you 2 weeks, so it won't be due for another 2 weeks before the class will be on that Thursday. So a lot of time. I wouldn't wait because we're going to start to cover material that looks nothing like these, right? This is just based over the material that we've covered. So I want to give you a long time though, because I know we're still kind of getting used to this program. I anticipate you having questions. I had like 4 or 5 people stop by my office yesterday. We kind of worked out some of the problems in Stata that they were having. It's difficult for me to kind of give advice on every single device. So if you're still having issues with those, please feel free to stop by my office. We can get those worked out so you can start working on this assignment and also some of the stuff that we're doing in class. I might have said on Tuesday, because we had Labor Day, my office hours are usually Monday. I was going to move them to the same time slot, but my Fridays are open for meetings, and lo and behold, I got a bunch of meetings scheduled. But I should be there tomorrow from 10 to 1, so the same amount of time, just a little bit earlier in the day. If you want to stop by, you start working on this problem set, you have run into some problems with Stata, it'd be a good time to kind of come by and troubleshoot that. Okay. Other than that, I was told, and I believe, let's see, put this up as an announcement. Probably saved it tonight. I will get up. I have a Word document that has 2 additional kind of solutions to if you're having issues still with Stata. So if you can get to the IU anywhere, if you get Citrix workspace to where you can at least get to this point, there is, under account settings, this option. So once you've activated it, if it's still not working, you can go to change. And there's this, I'm not going to select it because it's running fine. But if it's not working for you, trying to use this light version, it should work and it should have all the capabilities of what we need to do in class. But for some people, that should kind of solve if you're not able to open Stata correctly. Like it gives you the little thing, like it looks like it downloads and it says, I think it's an ICR on the end, like the extension. So using this light version, I was told by the IT department, often helps alleviate that problem. Okay. Also, as always, kind of clearing out. So if you want to use a different web browser than you usually do, because I can't remember if you clear out your cache cookies or whatever, you've got like passwords saved. I don't want you to lose all those. So maybe downloading a web browser that you usually don't use. So if you usually use Google Chrome, download Firefox, and then you can kind of clear out the cookies there and not worry about losing passwords or anything like that. That's also something that kind of might help. But I'll have, there's another solution. It's essentially kind of like getting it to the light version. It's just on different computers. You have to do it slightly differently. So I kind of have a step-by-step Word document. I'll get posted up after class, maybe even between this section and the next, so that you guys can kind of try to troubleshoot that. If you're still having issues, like I said, stop by. If you want to Zoom, you probably, screen share and kind of help you even via Zoom if you're available during that time as well. So you have to hike across campus, so it's going to be like 87 degrees or something. Okay. Any other questions on state or anything before we jump into material here today? So you'll see that first problem set, first quiz pop up. Like I said, right around 1 o'clock today. Okay. All right. So we left off thinking about sampling distributions. So we might have ended class. We'll just kind of do some review, start again with it. We calculate a sample mean the exact same way we did a population mean. The only difference is the notation, because now instead of dividing by the number of observations in our population data set, we're dividing by the number of observations, lowercase n, in our sample data. Okay? So regardless of the size, the distribution of our sample means is always going to be centered around that true population mean. Or said differently, the expected value of this sample mean should be centered around that true population mean. Okay? So if this is true, we say that our sample is unbiased. If the variance of our sample mean, so let's say I took 1,000 different samples. I calculate the sample mean for each one. I then have a data set with 1,000 different sample means. Well, we can imagine how in Stata, I could very quickly find the variance of that new variable, right? Those 1,000 sample means. The variance of those sample means will always be the original variance of the data you were sampling from, divided by your sample size. So this is where we said, as I get a higher and higher sample size, what's happening to the variance of my sample means? Sample size goes up, what's happening to that fraction? Yeah, denominator's larger, it's decreasing, getting a smaller variance. Well, that's good. That means that it's more likely that when I get a sample mean, there's a higher likelihood it's going to be centered around what that true mean value is. So this will be a kind of reoccurring theme. Larger sample sizes are generally always a good thing. Okay. So this is what we call consistency, right? If the variance of our sample means is the original variance over our sample size, we would say this is a consistent estimator. Okay. I've got some values here, and I left a blank slide, so we'll jump right over to Stata kind of early on here today. I'm gonna make this a little bit bigger, and we'll zoom in just a little bit more so you guys can kind of see this. Knowing that we can't save these settings. Okay, so I've got kind of my global here. You don't have to use a global pathway. So today we'll start out using just a .dta file. So these are Stata files. So the way I was explaining it to people, some people stopped by my office yesterday, like Excel, the way it stores the exact same data, it makes the file larger. This somehow, and I don't understand the technical side of it on the back end, but essentially condenses the data so that storing it is like a fewer number of bytes, right? So it doesn't bog down your machine working with really large data sets. So instead of defining this global and then running this first line of code, when you guys are working along through these do files, if you want to execute the do file yourself, you're not going to have the same pathway. And so if I didn't put this global and I just left in here, you can't pull stuff off my OneDrive, right? Or my iDrive. Now, once you download that file so that NBA height data is on canvas. You would download that, then move it from your downloads to your OneDrive, right? Once you have it in your OneDrive, you can go to the program, state of program, click open. There's that, I dragged mine onto my OneDrive. So I'll click that height data, hit open. It'll tell me the code that I'm using. So there's one thing I want to point out here. So this is great. I could then copy, so I don't have to go through the interface again, just to make sure I have this saved. Paste it, put it on different lines, so I have to get rid of that. If I had a bigger screen, that would be helpful. That's another thing. Honestly, when you're working on these projects, or I call them projects, when you're working on these homeworks, I would find a university computer or be at your apartment where you can have, if you have an additional monitor, doing it on a laptop like that size is going to get real annoying just with like the size of having the program, the do file. I would try to kind of get a larger visual space, just makes it a little bit easier to work with. Okay. So once you have, I've got this, I could always rerun this again. There's going to be one problem. So this will do the exact same thing as if I were to define this global and then use, okay, this is the folder my files are stored in. So you should just create a folder on your OneDrive that is like E371 materials. And then that way you can always just have that path to go to that folder, and then you're just dropping all the files you want to use into that folder. So your path would be your own kind of iDrive and whatever name you're calling the folder, the materials you're putting it in. Or you can always just go to file open. If you want to do it that way every single time, then copy and paste the code over, by all means, go ahead and do that. Right? Now, if I were to try to use this global, so this is going to be for my specific OneDrive, and I've got things not just in one folder, but a bunch of different, tiered stuff. When I go to use this, if I were to leave off, so notice when I ran this line of code, it didn't include this clear command. So if I didn't include that, and I tried to run this again, open up the data, here, let me see. It should give me an error. Might be defaulting to this because I'm using my global. And I think it might be on the light version. Sometimes you'll need to put in this kind of comma clear, because what it won't do is it has data that it's already opened up. It doesn't want to kick that data out unless you tell it to. So you can't like reopen the data set twice until you clear out the old data. So this comma clear command is going to be necessary sometimes when we're reopening data sets. I think here it's not, because I have to like make changes to the data. So I think if I were to leave this off, okay, do that. Then I go keep. I try to open this up. There it goes. So once I make changes to the data, it's like, well, I'm not going to open a new data set because you haven't saved this, right? This .dta file, you've made changes, but you haven't saved it. We're not sure that you really just want to get rid of it. So in that case, I'm going to have to make sure, okay, I'm telling you I want to get rid of it. So how do I tell it I'm getting rid of it? I put the comma clear. Now, when I go to run this, oh, there we go. It's being slow. Oh, I want you to be able to see it. Now it is able to open that data set. So if you're getting in that error, it's because you haven't cleared it out.
Can you clear on a different line?
Yeah, I think I have later on in this program. I think if you just type the command clear prior to it, I will make sure, make my changes, and I run, whoop, I'll highlight this, not moving, and I run both lines of code, that'll do the same thing, right? So I don't have to put the clear command, I can put the clear command above it if I want to as well. There's just multiple ways of doing the same thing. I always just kind of like to put it on one line just to make it, succinct. Any other questions on that before we keep moving here? Okay. So I'm going to just keep two variables here, which is the player name and their height, and then going to kind of summarize. We can look at what's the original mean of this variable. So it's around 79.14, and then the original variance is 12.6-ish, right? So this is the original data. It's got all these different NBA players and their height, right? It could be any height data set, right? But I'm going to use it to prove what I was telling you about our sample means being unbiased and consistent estimators. So I've got this little thing here. I'm gonna clear out some programs. You should never have to worry about this. I'm not gonna make you actually write programs in Stata. So what I'm about to do maybe shows you the power, but I'm not gonna ask you to do anything like this, all right? The stuff that problem set is going over is things that we already went through, mainly things from that review of statistics do file. This is just a kind of way for me to show you what's true about the sampling distributions. So you can write programs in Stata. So first of all, I had a couple people do stuff like, how many of you ever used R or Python? There's a handful. So you can like write programs in. You can do the same kind of thing here. So I have this program called ybar, which is essentially the sample mean. I'm just, here's some different syntax stuff. I'm gonna open that height data. I'm gonna sample, right, 10 different observations. So this randomly samples them. It's then going to kind of create this new variable, which is the height variable. I'm gonna summarize it. And then basically when you summarize this variable, it kind of stores. So when we're looking at this output, and this is probably getting way more into the weeds than you guys need to know for this class, but it like stores this stuff behind the scenes. So even though you do have this visual output, you can like call these different things to pull out of this the mean, or you can pull out the 10th percentile, or you can pull out these different values that you're seeing on the screen. So that's what this part of the program is doing. It's kind of pulling out, it's creating this scalar, which is just going to be pulling out the mean from that summary command. So all this is what I'm essentially doing here is I'm labeling this program, and all this program will do is randomly sample 10 observations from the data and then store them as a separate data set. So if I go down, so I'm going to define this program, first of all. I'm then going to go down, and this was what I was showing you just about the homework, so we'll get rid of that just to not muddy it up. Now what I'm going to do is I'm going to take this kind of program ybar, and essentially what this line of code does is it's going to simulate, it's going to store the sample means every single time I run this program, and it's going to do it for how many repetitions? 1,000. So essentially what this will do is it'll use my program that randomly sampled 10 people, calculate the sample mean, store that sample mean. They'll then go and randomly sample another 10 people, calculate the sample mean, store that sample mean. So, we don't have to do all the footwork, right? Although, go out and actually, randomly choose 10 of the observations, do all the hand calculations ourselves. So if I do that, I'll take a second because it's 1,000 different simulations there. Okay, it's ran it. I can't see this variable, but I've so when I'm storing this and look at the actual data, here were the 1,000 different sample means from a random sample of 10 of the people in the data set, okay? If I then go to summarize this and I put the comma detail so I can see the median, things like that. Now when I look at this output, notice the mean of these sample means is almost exactly what it was before. In fact, we go back, what was it before? 79.14343, 79.14307. So it will be a little off, right? It's very, very close though. We'll talk about why in a second, why it's a little off, but we're getting an unbiased estimate, right? The mean of our sample means is exactly that population mean. Well, what if instead, oh, and also to point out, the variance was 1.3. I chose the nice number of 10 because this was what, 12.59. So I should be that the variance in my sample means is the original variance divided by my sample size. So 12.59 divided by 10 should be what, 1.25. It's a little off, right? It was 1.30 instead. So I mean, we're a little still not consistent, right? But that's because we were only dealing with a sample size of 10. We'll eventually today talk about, you might remember from 370, what sample size do I need for this to hold? It's kind of a magical cutoff number, 30, right? So, and we haven't talked about that yet, so I'm not expecting, but just trying to pull some things. So I'm gonna do this exact same thing again, but now I'm gonna create this program, so clearing my programs out. Now it's gonna be it randomly samples 30 people, right? So if I were to randomly sample 30 people, and then once again, run that simulation, 1,000 different sample means, storing them as a new data set. So I've now got 1,000 different sample means. I then go to summarize those. And just to kind of make a point, I can always use the shorthand. So once again, 79.14 was the original. I'm a little off, but I'm really, really close. And then my standard or my variance 0.43. Well, 12 divided by 30, is about 0.4. So we're getting closer and closer, right? We're still a little bit off. Now, the reason why we're a little bit off here is because I'm only taking 1,000 different sample means. In order to truly prove this to ourselves, what we would actually need is an infinite number of sample means. That's not, we can't really do this data proof because we truly can't get an infinite number. But the larger simulations I already get, so if instead of 1,000, I did 10,000 sample means, these would be even closer, right? And then I can kind of show if we go to 100, it's getting even closer and closer. So the sample size will also play a role. So I'm going to randomly sample 1,000 different sample means, store them. They're all of size 100. Then calculate the mean and the variance. Maybe still thinking. So while we're waiting for it, once I have this larger sample size of 100, well, my sample mean should still be around 79.14, but my variance of what it was like 12.6, now it gets divided by 100, I should see 0.126 as the variance of these sample means. Sure enough, 0.123, hey, it's pretty close. And then 79.1 rounded to the second decimal 4, I'm getting that population mean as well, okay? So this is kind of just proving this theory, that the mathematical theory behind this. You can kind of prove it to yourself with data. Now, obviously, the numbers are going to be a little bit off, like I said, because we're only doing 1,000 simulations as opposed to 10,000, 100,000. The more simulations that we would do, the closer and closer we would be getting, okay? Any questions? And anything here. Also, hopefully, like I said, I'm not going to push you guys quite this far to like create your own programs, but you can kind of see the power of what you can do here in Stata. You can run a lot of different simulations. This might be something you want to do if you're trying to predict like GDP growth, things like that, based off of historical data. So outside of this class, hopefully by the time we're done, that would be kind of the next level. Okay. All right. So if we're looking at these numbers, it's getting pretty close, right? So we looked at these in Stata, we're getting pretty close. Start from here. So why were they a little off? Well, technically we need an infinite number. I already mentioned this, but also to the question I asked before, especially that first time we were only sampling 10 people. Truly, we don't know if the original height variable I showed you last class, a lot of height data looks pretty normal, but it might not be. And if something starts out and it's not normally distributed, then the mean of my sample means might not be normally distributed as well, and it might be biased or inconsistent, right? What might not, those things we said are going to be true might not hold. So we need there to be at least a sample size of 30. As we get larger and larger sample sizes, that sample mean, the mean of our sample means just gets closer and closer to the population mean, and our variance gets closer and closer to the variance over the sample size. So doesn't matter how it starts out. Distributed, as long as we can get a sample size over 30, we know that our sample means will not only have a kind of the mean be equal to the sample mean, they'll also be normally distributed. So what I'll show you here real quick. Well, I'll show this before we go back to Stata. Whoop. I scrolled too far. There we go. So this is just, I think I pulled this from an old textbook because I've always really liked this example. But you can see no matter what the original data starts out as, these are like wild distributions, right? One of them is, I don't know if you talked about the uniform distribution in 370, but it's just everything's equally as likely. You've got, this kind of parabolic looking weird distribution. So all the data here starting out not normally distributed, we sample from these data, these original distributions, even at 2, okay, these aren't looking normal yet, right? But they're looking different. So these are going to be what the distribution of our sample means would look like if our sample size was 2. And then what if our sample size was 6? What would the distribution of our sample means look like? Well, now you can see here, even at 6, they're starting to get pretty normal. Like they look like a normal distribution. Now, some of them, like the second one's shifted a little bit, right? We've got some skew still to some of these. But once we get to 30, all of these distributions of our sample means should all be normal, and they're centered around whatever the original mean, that's what this red line is, right? The original mean of the data we sampled from. So it doesn't matter what the data starts out as. So what's one command, maybe, I know that we're not super familiar with all these, but I did one last class. If I've got these 1,000 different sample means, and here we've got sample size of 1,000, so they really should look normal. What was the command we looked at last class to get a quick idea, a snapshot of the distribution of data? It was just that hist command. It created a histogram. So I'm gonna just put the histogram there, and I'm gonna put it in my do file because I didn't necessarily have, that wasn't part of it. I just want to show you that we can do this. Look at this. I mean, this is it's hard to draw a normal distribution better by hand, right? So as long as we're getting a sample size over 30, the distribution of our sample means could always be normally distributed. And in fact, just to kind of prove that to you, since we've got the code here, we can just rerun it. Let's do a sample size. Let's do 31, right? We have to have over 30. So, I didn't clear the programs out. So hopefully, once we get this, now if I use that hist command to look at the distribution of these different means I stored, pretty close to normal. It's not perfect because we've got these histograms don't allow things to be like completely continuous. But if we were to kind of make more of these like more narrow bins, this would look a lot more similar to kind of a normal distribution. Okay. And once again, technically, I wouldn't just need 1,000, I would need an infinite number to kind of show this. Okay. Any questions over this idea before we keep moving here? Is this sounding familiar? Hopefully. And we can go back and look at those samples, those sample means or unbiased, also consistent. So we've got this knowledge now of our sampling distribution. So everything we've done before today was all about population data. Now we're thinking about sample data. So I know my sample distribution. If I can get a sample size over 30, will be normally distributed. The expected value of those sample means will be the original mean of the data I sampled from, and the variance will be the original variance of the data I sampled from divided by my sample size. So how do we calculate? So if I'm looking here, what's the problem? If I have a sample, how do I know what the population variance is? The whole reason I took a sample is because I didn't have the population data, right? So this is great, but more often than not, we don't have the population variance, right? So what we would actually need is, well, what's the variance of the sample data, right? That's all we can do. So that's why even the stuff I was showing you was a little bit incorrect because it wasn't factoring in that kind of, we were looking at sample variances there. So we'll, instead of writing the standard deviation of our sample means using that Greek lettering, because we're calculating that based off of only a sample variance, that's the best guess we have of what the population variance is. We're going to kind of use S, kind of notate, we're calculating the standard deviation of our sample means based off of, actually, I just want to correct this because I'm away from those typos. This was supposed to put, copy and paste it, and it didn't carry my bar over. There we go. So it still looks like the standard deviation of our sample means. But now we notate it with an S saying, okay, yeah, but we were calculating this based off of sample data, right? A sample variance as opposed to. So it's just a difference in notation indicating we weren't using a population variance to calculate this, but instead using a sample variance. So what's one problem going to be if I try to use a sample variance here? Even if it's my best guess of what the population is, let's say I take a sample and it's, lo and behold, it's perfectly the exact same variance or distribution as what the population would be. When I calculate it by hand, and I don't think we went through this maybe necessarily yet, but maybe you remember, when I calculate a variance, I'm dividing, taking the deviation squared and I divide by capital N for a population. If it's a sample variance, I add up all the deviations squared, but I divide by what? You remember the difference in calculating a sample variance versus a population variance? I don't divide by the number of observations. I divide by the number of observations minus 1, right? And then, so even if I had data that was exactly perfectly matching up to the population data, because I treated it was from a sample, I should have been dividing by N instead of N minus 1. It's always gonna be a little bit off, right? So how do we account for this? We don't use the standard normal distribution. So remember, when we're wanting to standardize variables, we're subtracting the mean, dividing by the standard deviation, but if all I have is sample means and sample, I only have samples, variances or standard deviations, then it's not gonna be quite standard normally distributed, but it will follow a normal distribution, and it's a specific set of normal distributions, which we call the student t distributions. So it's a family of distributions. I think I have a visual here I want to get to, but before I should mention things. It's a little bit more spread out than the standard normal, right? So if it's more spread out, you gotta think about, is it gonna be a little bit flat? The tails are a little bit thicker, right? Or it's a little bit higher. I want to think about it that way. We're also gonna have this new thing called degrees of freedom. So this is the idea that if I had a small sample, the fact that I was dividing by n-1 instead of n, so if I divided by 9 instead of 10, that's gonna cause a much larger difference than if I was dividing by 999 instead of 1,000, right? So as I have higher degrees of freedom, if I have a higher sample size, this student t distribution is gonna it's gonna matter less. It's gonna be getting closer and closer to a standard normal distribution. In fact, if we did have an infinite sample size in theory, that student t distribution would be the standard normal. Okay? So what does it look like kind of visually? And I'll come back to this here in a second. It's gonna look something like this, right? So I've got degrees of freedom here. First of all, what would my sample sizes be at degrees of freedom of 20 and 5? So the degrees of freedom is n-1, 6 and 21. We've got sample sizes. All right, so the sample size is going to determine which student t distribution you need to use. Okay? So the standard normal I drew up here, we said the student t is a little more spread out, so it's going to be a little bit kind of squished, right, flatter, less likely. Remember, all these distributions are kind of telling us here's the probability I see values near the mean. I made the mean 0 here just to make it easy to think about. Or sorry, I didn't make it 0 easy. This is the standard normal distribution, so we know that mean is 0. So these values around 0 are a little bit less likely, or said differently, it's less likely we see things fewer standard deviations away from the mean, but it's more likely from these student t distributions that we see values that are higher numbers of standard deviations away from the mean. And then as our degrees of freedom, our sample size gets smaller, it just becomes less likely we see things that are not many standard deviations away from the mean, more likely to see things that are further or higher number of standard deviations away from the mean. Right? Excuse me. So it still has the same properties as the standard normal, that its mean is 0, right? And it's symmetric, so the mean is equal to the median is equal to the mode. But it's a little bit more spread out. We already mentioned this. And I said, if we did truly get it to be infinite, that's when it would theoretically, not theoretically, that's when the mathematical proof would be that it is exactly equal to the standard normal. But in practice, if we just get over 100 degrees of freedom, we're out to the third or fourth decimal that is a difference, right? So generally a good rule of thumb, if you can get a sample size over 100, you can basically just treat the student t distribution like the standard normal, because it's converging towards it, and it's already so close to the degrees of freedom of 100, you can't even really tell the difference if you're just looking to like even the third or fourth decimal. And in practice, like our data sets are going to be way more than 100 people. So yes, I'm setting this up and just kind of mention the student t, but in practice, we really are going to be looking at values that come from the standard normal distribution. We went through this. This is kind of a nice way. So when we're looking at that standard normal, last class we said we could look up using that z table different values. So if I looked at the value of 1.96 as my z-score, the area under my standard normal curve and to the right of that is going to be 0.025. Okay. However, for my student t distributions, if I keep using that same value, what's going to be the area under that student t distribution curve but to the right? Well, if my tails are now a little bit fatter, those areas are going to be a little bit larger. Okay. So if I want to guarantee, to our point, last class, the example was like what score would be put you in the top 10% of the class. Well, if you try to use this many standard, that's not going to be right. All right. You actually need a value that's a little bit higher to give you that kind of 0.025 in that right tail. So what do we have? We have a student t table. How does this work? Just before I show you that. here you look at your degrees of freedom. I put one up on Canvas. There is a PDF, and it doesn't have these big jumps here. Like it goes from like 1 to I think it goes from 1 to 20, and then it starts making jumps of like 10, and then it kind of goes from like 50 to 80 to 100. So it doesn't have like every single possible integer value up to 100. But for the sake of this class, I won't ever ask you about degrees of freedom that wouldn't be in that table, and we're not going to really use it a whole lot, like I said, because our sample data is so large. But you can see before we said if we keep using the same value, that area in the tail is going to be larger. So how do I make that area in the tail what I wanted it to be, which was instead of like 0.06, 0.025, I need to choose a higher value. So you'll notice to get that same 0.025, as my degrees of freedom is going up, the value that I need can be lower and lower and lower, and is approaching that value that I needed from the standard normal distribution. So even at kind of 100 though, we were already at 1.98, we were within 0.02. Just in practice, like I said, we're okay being that close. Any sample size or degrees of freedom. So sample size of 101, degrees of freedom of 100, anything over that, we're just going to use our standard normal distribution values to approximate. Okay? So you'll see these values pop up a lot, all right? 0.05, 0.025, and 0.005 in the tail. Once we talk about hypothesis testing, confidence intervals, these are some of our benchmark values. Okay, and this will make a little more sense after we kind of get through covering those materials today. Okay. All right. Any questions? You guys are being a little bit too quiet for my liking. I get worried when I don't get questions or anything. We're good? Looking familiar? Okay. So hopefully you also covered hypothesis testing. You remember kind of what that is. We're going to say, okay, look, we've got this sample data, and we can see what the mean is from our sample data, but you know, it could be a little bit off from what that true population mean is. I might want to know, can I rule out, or can I say that the true population mean based off of the sample data I saw, that that can't be true. So for example, if I see a sample mean, I sample a bunch of students here at IU, I see the average number of days, or the average number of dollars spent at the bars each week is $150. Well, I mean, that seems pretty exorbitant to me. I'm going to guess that, you know, I can probably rule out if you told me, well, no, the students, you know, at IU spend $10 a week at most. I look at my sample data, I'm like, well, I've got sample mean here of 150. I can probably rule out that value you just told me, right? So we're going to use hypothesis testing, and based off of our sample data, how can I rule out different assumed true means? And when we say assumed true, generally, this is like things we're trying to disprove, right? I'll set examples up where it's like, you know, the American Medical Association tells us this. We take a sample, we find it's this. Can we tell them they're wrong, right? That's essentially what we're doing. Now we have 3 types of tests. We're really going to focus on one major type of test here, which is going to be the two-tailed test. It's going to be the most useful for the majority of what we do this semester, which is going to be linear regression. So when we're looking at linear regression, 99% of the time, we want a two-tailed test, okay? But there are one-tailed tests. So what we can do is say, okay, look, I'm going to start out assuming, this is my null hypothesis, H subscript 0 just notates this is going to be what we assume is true. So what I'm going to assume is true is that the true population mean is equal to, and this mu subscript 0 is always going to be in practice some value. So in my stupid example, I would have H subscript 0, the true population mean is equal to 10. That's what I was told. I have sample data that is inconsistent with that null hypothesis. Or I found sample data that went against the null, but supported what we call the, I thought I had it, alternative hypothesis. So here's my null. The alternative hypothesis is going to be the complement of the null hypothesis. So basically the exact opposite, right? So if I assume that that true population mean is equal to 10, my alternative hypothesis, H subscript 1, is that that true population mean is not equal to 10, right? So it's the exact opposite of my null. Or up here, we can have 2 different types of tests, which we call right and left tail tests. Maybe I assume that the true mean is less than or equal to a certain value, in which case the opposite of that would be I assume that the true mean is greater than that value. right? And vice versa. So there, we only care about like one direction. So we call these one-tailed tests, right? We're only kind of focused on, can I say that it's not, did I find sample evidence that went against it being less than or equal to a value or greater than or equal to a value? This final two-tailed test, I'm saying that I find sample evidence basically just says it's not equal to that one value. It could be on either side, but it's inconsistent with that exact value being the true population. Okay. And this will have some implications when we start to talk about things like critical values and p-values here in a second. But this is our kind of general notation for our null and alternative hypothesis. You might sometimes see this written. If you like to Google, like, I don't know, browse set resources. Sometimes people just use H subscript A. In fact, I think that's probably a better way to do it. But like the true stat stuff, they'll usually use kind of 0 and 1. But A, kind of the alternative hypothesis there. You could also kind of use that notation. Okay. So we've got everything we need now to start doing these hypothesis tests. So I take a sample. Now, my example, I found the average money was $150, right? How do I standardize that? Well, in general, you subtract the mean. So if I'm calculating a sample mean, I'm actually going to be subtracting the mean of the sample means. Right? I'm no longer looking at just a variable, I'm looking at a sample. So the mean of my sample means is whatever the true population mean is, but I don't know what that is. I don't have the population data. But if we're trying to test different values, we're going to say, okay, we're assuming this is the true population mean. So in my example, I'd have 150 minus 10. That was the assumed true value, the value that I was told that I'm trying to disprove. Okay? So we no longer have the true mean, but we're still standardizing it. Assuming that that is the true mean, we should subtract the mean from the sample mean we saw. We then would divide by, in fact here, just to kind of make sure I'm being clear about where this is coming from. If we were going to standardize a variable, before we were saying, look like this, right? Well, now we're trying to standardize a sample mean. So we're going to take the sample mean value, I want the standardized value. We'll kind of use Z to notate that since we're doing multiple things here. Well, what's the mean of my sample means? I don't know it, but I'm using that assumed true value, right? And then what would the standard deviation of my sample means be? So if I wanted the standard deviation of my sample means, well, that's just going to be the square root of whatever my sample variance over my sample size is, right? So, right, because this would be how I calculate the variance of the sample mean. I only wanted the standard deviation, so I had to take the square root. So all of this information, I pull out from the data that I sampled from, right? I've got my sample mean, I've got my variance from that sample data, I've got my sample size from the data set. All of that I get from my sample, and then I have this assumed true mean that I plug in. I'm treating it as though it is the true population mean. This would then tell me how many standard deviations away from that assumed true mean is the sample evidence I found, right? So we can start to think about, okay, if I turn this into a z-value, I get, or a z-value. I'm trying to relate this to things we already talked about. So this was the idea of standardizing it. Instead of a z-value now though, if we're using sample variances, this isn't coming from a standard normal distribution or z-tables, it's coming from our student t-tables, so we generally now start calling these t-values, right? They represent the same thing, which is how many standard deviations away was the sample mean from, now we don't have the true mean, but from this assumed true mean. So if someone tells me that the average money spent is 10, I find 150 for my sample mean, I've worked this out and it ends up being 4 standard deviations away, that's pretty unlikely. What you're assuming to be true based off your sample evidence has a very low probability of occurring, right? It's 4 standard deviations away. Now, if I turned it into a t-value and I found it's like 0.5, okay, it's still inconsistent with what we assume to be true, but only being half a standard deviation away isn't near as far. It's possible that if that was the true mean, we did see this from our sample. Okay? So this is kind of a general kind of intuition. see here. So we'll do a critical value approach, and I'll kind of give you a visual to go along with this as well. So what we're then going to do is, okay, look, we know we can calculate these, what we end up calling kind of test statistics, these t values, right? So based off of this test statistic, which is just representing a t value, it's the number of, the only reason we call it something different is because we're not subtracting the actual population mean, we're subtracting an assumed true population mean. So this is going to be our test statistic that we're using. Now that I know how many standard deviations away my sample evidence was from this assumed true value, I can kind of create these cutoffs to say, if it ever gets to be greater than 2, I'm okay rejecting the null, right? If it ever gets greater than 3, I'm okay rejecting the null, right? So these are going to be what we call critical values, right? They're just going to be the point at which if my test statistic becomes even larger than this, I'm okay rejecting whatever I assume to be true, because I've now gotten to be a certain number of standard deviations too far from that assumed true mean for it to really make any sense. Okay? We're also, what these critical, we don't have to just have one critical value. We generally talk about multiple critical values. Okay, so I'm gonna kind of draw this out. I think I've got some slides to go with it, but I think I can do a better job. So let's do a right tail test to kind of start out with. So if I'm thinking about, here's kind of the distribution of my sample means. They should be normally distributed around whatever that true population mean is, right? That's kind of what we started all those simulations off of in the class. We don't have that, right? We're assuming that the true population mean is a certain value. So if I see sample evidence that's, say, out here, what I'm wanting to do is say, okay, look, here's my student t distribution. And we'll assume that we have a large sample size, so I can use the numbers that I remember, which is if we use a standard normal to kind of approximate, the value that would give us, let's say 0.1, about 1.28, right, would be kind of the cutoff value. So if we have a large sample size, we can use these standard normal distribution values to kind of approximate it. When we looked up that area of 0.1 in our table, we find that the value, the z value, right, we're using the z value to approximate here, and the t value would be very close to that, even if we were to use the t table, will be about 1.28, 1.29, right? So we'll use kind of 1.28 here. That would kind of give me an area of 0.1 on the tail. This is going to be what we're going to call alpha, right? So alpha says, okay, if I were to see anything out here, so if I found sample evidence that corresponds to a test statistic, and let's just say this was 1.5, right? If it corresponds to a test statistic that is anywhere to the right of my, what we call critical value, that gives me this desired area in the tail, I'm okay rejecting this assumed true mean. Why? Because if I see anything even further than this, the probability I saw this test statistic or this t value or anything further away from that assumed true mean, that probability has fallen to be less than 10%. So when I'm choosing alpha, what I'm essentially doing is saying, look, I want it to be that if the sample evidence I found, I want there to be less than a 10% chance I saw that if the true mean was what I assumed the true mean was. So if I get a test statistic 1.28, well, there was a 10% chance that I saw that. Like that's exactly my cutoff. Seeing anything further than 1.28, that probability falls below that threshold I set. Right? I was okay not rejecting it as long as the probability I saw that sample mean was like 15%, or probability of 0.15. I'm talking percentages here, but probably 0.15 or percent of 15. So once we find that value that gives us our desired alpha, or kind of the value we're okay with not rejecting it, our rejection region for a right tail test is finding a test statistic anywhere to the right of that critical value. I could then do a very similar thing. Like I said, we're mostly going to be using two-tailed tests in this class. So you can think about here, maybe I start out with a null that it's equal to a certain value. Well, now I find sample evidence, let's say It's out here. Thinking about my t-values here. So once I kind of turn this into a test statistic, or subtract the mean, divide by the standard deviation of my sample means. If I still wanted that same alpha, that same probability of seeing sample evidence as inconsistent with what I assume to be true, or even further away, I'm okay with there being like a 10% chance. As soon as like it falls below 10%, right, this probability of 0.1, then that's so unlikely that what I assume to be true probably isn't true. The difference with a two-tailed test is now, because evidence on either side goes against the null, when I'm thinking about choosing my kind of critical value or my cutoff values here, I don't want 0.1 in this tail, because seeing sample evidence that was above my assumed true mean is inconsistent with a null, but now also seeing sample evidence below is inconsistent with the null. So now I need to have a pair of critical values. So when we have a two-tailed test, I still want alpha total kind of outside, like we kind of call this in my rejection region, but now I have two regions. Now that critical value will be the exact same value, just one's positive, one's negative, because the student t we said is symmetric, so right, folds on top of itself. So the same area, we'll have the same area to the right of the positive value as the same area to the left of the negative value. So now we think about, we're finding critical values for a two-tailed test. It's not going to be the value that gives me alpha in this tail. It's going to give me half of alpha in each tail. That way, when I add them both up, I've got two tails. Total would be the alpha that I chose. Right? So with a two-tailed test, it makes it a little bit harder to reject the null, because when I have a one-tailed test, notice that value would be something like 1.28. I think if I'm remembering correctly, the standard normal for a two-tailed test, to get not 0.1 in each tail, but half of that, right, 0.1 over 2, to get 0.05 in each tail, the value is not 1.28, it's 1.65. So now seeing that same sample evidence for a two-tailed test, maybe now I failed to reject the null. It didn't quite make it past that cutoff value. Okay. Excuse me. Any questions on that idea before we keep moving here? Is this looking somewhat familiar? Okay. I swear next week I think we'll get to what I find to be more interesting things. So, oops. This kind of has like a summary. When I'm looking at a right-tailed test like I drew out for you, it's going to change our inequalities because I'm dealing with positive values on the right side. So there, my cutoff, here's my critical value. It's if my test statistic is greater, right, or to the right. However, I was looking at a left-tailed test. I've got my cutoff that gives me that alpha in the left tail. There, I actually am looking for a test statistic that is a larger negative value. So technically, we're saying, is that test statistic less than, because a larger negative value, the way negative values work, -10 is less than -5. I always say, like, just a good practice, doesn't matter if it's a left, right, or two-tailed test, it'll always prevent you from making them, getting you confused. Just treat it like a two-tailed test in the sense that you're comparing the absolute value of your critical value to the absolute value of your test statistic. In that case, when you're using the absolutes, you only reject if the absolute value of your test statistic is greater than the absolute value of your critical value. And this will deal with the kind of weird, talking about negative numbers for a left-tailed test. It'll always make sure that you're just looking at just the magnitude of your test statistic. So, before I keep going, I'm using a term. Does everybody know what I'm saying by absolute value? All it means is drop it, like ignore the negative or positives. It just makes it positive, right? So by taking this absolute value, and that's what these two vertical lines represents, I'm just looking at the magnitude of the number, right? So this is kind of our general rule of thumb for critical values. And like I said, just always taking the absolute values, then you always just have, if the absolute value of the test statistic is greater than the absolute value of your critical value, you reject. If it's not, you fail to reject that assumed true value for them. Okay. All right. I kind of jumped the gun here. So we already did this. I did this already on the dot cam. But we can think about different values. Right? I'm just looking for what cutoff value from this distribution gives me that desired alpha in the tail. Okay. Here's a little bit more of a summary. I've got kind of our three benchmark values. So why did I say these numbers will pop up a lot? Well, because quite often the benchmarks we want to set, I only want to reject it if there was less than a 10% chance that I saw the sample mean I did if what I assume to be true is true. I only want to reject it if the probability of seeing the sample mean I did is less than 5%. Right? This is all, I'm talking percentages, but when we're dealing with a distribution, it's in decimal form. So we could just say, you know, the probability of seeing it was less than 0.1, or the probability of seeing it was less than 0.05. So these are going to be three kind of benchmarks, right? You think about them as 10, 5, 1% significance. Okay. Now for a one-tailed test, they're going to be the exact same value for your critical value, but one you're dealing with the right side of the distribution, so they're positive, the other negative. I already kind of showed you the caveat with the two-tailed distribution. It won't quite be the same numbers because the area in each tail is going to only be half of alpha. So you actually need the values that are going to give you 0.05, 0.025, and 0.005 in each tail. Because then when you add those together, right? If I add 0.005 from both tails, I get 0.01, 0.025 from both tails, 0.05. So it still would correspond to the 90, 95, 99% levels. Those are our three kind of benchmarks. Okay. Any questions before we keep moving here? I know I'm going through this kind of quick. Like I said, I know that you guys went through it before, so I maybe not going through it. Going through it a little bit quick. And then this is just kind of a summary. This is all the steps put together. We figure out what our hypothesis test, what our assumed true value is. We turn our sample mean into a test statistic. I wrote the test statistic a little bit different here, just to kind of highlight, because we're like taking the square root of the variance over the sample size. Square root of anything squared is just itself. So you can rewrite it. Like if you have the standard deviation instead of the variance, instead of going through the math to square it, this is the format of a test statistic you could use. It's just, like I said, just displaying it a slightly different way. But we can always go back and forth between variances and standard deviations because standard deviation is the square root of the variance. So when I'm talking about kind of these different alphas, they're always in decimal form. But when we generally say, do I reject this test? We typically say it is in percentage form. So can I reject at the 10%, 5%, 1% level? So really, you would take alpha, if I had an alpha of 0.01, I find the critical value, my test statistic is greater than that, I reject the null. I'm saying that I can reject the null at not the 0.01 level, but 0.01 times 100 or the 1% level. We're just moving from kind of decimal to percentage there. Okay. Questions on this before you? So here's kind of the listed out steps to this critical value approach. You figure out the null and alternative hypothesis, specify the alpha level you want, calculate your test statistic, then using this desired kind of confidence level, right? Using your alpha, you find your critical value. You want to think about where your rejection region is. We said for a right-tailed test, the area to the right, left-tailed to the left, two-tailed, area to the right of your positive, left of your negative critical value. And then if your test statistic falls in that rejection region, you reject the null. You reject what you assume to be true because the likelihood of what you found from your sample was so unlikely that it's probably what assumed to be true isn't in fact true. Okay. I think I want to use the rest of the class here. So we got 15 minutes. Not gonna quite get where that's where I want to today, but I think that's okay. Let's try this out. It might be a little bit behind, but if not, we can kind of use this. So, so this is how classes. So this is how we'll use kind of the in-class quizzes. I will, in class, switch this over so that we now can go to the quizzes tab, add it here for in class. You could just go to the quizzes tab. You should now see this in-class quiz 1, right? You'll kind of open it up. I'll open it up as well. I'll preview it. You can kind of see, okay, there's 3 different questions. Now, we haven't worked through question 1. I don't think we're going to quite have enough time to get the confidence intervals, but I wanted to make sure I at least start using this in-class quiz and we can kind of see how it's going to work in practice. So I would open this up. You know, the last point, or the last question point, is worth 2.5 points. It's just like you get half the credit for this in-class quiz by simply being here today. So this was the idea of kind of me rewarding you for effort, for showing up to class and trying to kind of, you know, incentivize attendance, okay? So you start this quiz. Hopefully everybody gets that last one correct. All you have to do is click on the yes button. We didn't talk about confidence intervals today. So if you want, just ignore that. Then once it's submitted, I can go on and give everybody credit for that question who at least had a response to the other ones. But we can kind of work through question 2 as well, okay? So generally what I'll do is I'll say, okay, look, we've covered this material in class. Here's some questions related to it. Work with the people around you, try to kind of walk through these and then solve this problem, okay? Now, like I said, I'm running out of a little bit of time, so I might be really nice some days, just kind of walk through them with you, because these are also going to be like good questions to go back to look at before you take the quiz, okay? So this question that we can answer is, suppose you assume that the mean IQ is 105, you take a sample of 50 individuals, and you find a mean IQ of 102. You have kind of a population variance of 144, so I'm making it a little bit kind of easier here so that we can just use the standard normal distribution values instead of having to even approximate them. I might actually use chalk here so we can walk through this. So what levels of confidence can you reject the null hypothesis at? So the first step is figuring out what our null hypothesis is, which is that the mean is equal to what value? So what value are we assuming that this population mean is equal to? 105, or is it 105? Yeah, I assume that the mean IQ is 105. I took a sample, so I can think about it as my sample mean, or I think the notation I've been using was Y. So the sample mean is 102. My sample size was what? 50. Here I've got a known population variance, so it makes my life easier. I'm calculating a test statistic from the standard normal distribution. So 102, or no, 144. 144. Thank you. The more you help me, the more it's more likely I have the correct answer here. So what I then think about, I have this what? I have a two-tailed test, right? And I can kind of mix some of those steps up if I want. I can calculate the test statistic first and then the critical values. Generally, I think finding the critical values first, it just makes a little more sense, as hopefully we'll see here in a second. So I know that for a two-tailed test, I'm looking for a pair of critical values that gives me, what's my alpha here? So I want, oh, I didn't get one. We want to do one at every single level. So I'm actually going to have our 3 kind of benchmark values. So alpha of 0.1, 0.05, and 0.01. Remember, I have a two-tailed test, so I actually only have half of alpha in each tail. So the values that are in my tails are going to be 0.05, 0.025, and 0.005. Okay? Now, one thing that we can do, and if you have the student T table, you can open up the PDF that I put up there. I'm just going to use this one to kind of prove a point. Instead of using that standard normal, we're going to use these same benchmarks every time. So instead of like hunting, looking up the probability in the middle of that Z table, go up to find the corresponding Z value. The Z values you would find doing that will always be in this last row of the student T table. So it's almost like the Z tables are kind of in your student T table, at least for these benchmark values that we want. So we want an area of 0.05, 0.025, and 0.005 in our tail. Here's our 3 values that would come from the standard normal, that last row. Because that's last row, remember we said the student T is converging to the standard normal distribution. So that infinite row represents when it would be the standard normal. So here, I gotta kind of muddy this up a little bit, but let me me draw this so I give myself a little more room. So here, I've got, the furthest one was what, 2.58? So we'll do one at a time, right? Just start out so we don't get too many things on here. So what would my test statistic be here? So I now have kind of, here's my critical values. If I see anything that's any more than 2.58 standard deviations away from that assumed true mean in either direction, I'm okay rejecting the null. So what do I need? Well, I need to figure out how many standard deviations away, and actually here, I'm mixing up my examples. Because I gave you a population variance, we're still calculating a test statistic, it's just coming from the standard normal or the z-tables. How do I do that? I'm going to take my sample mean, I'm going to subtract what? So I would subtract the true population mean, but I don't have it. So what do I subtract? We go back. How do I calculate these test statistics? I take my sample mean, I subtract the assumed true mean, which here was what? 105. I divide by the standard deviation, right, of my sample means, which is the square root of my variance over my sample size. So does anybody want to help me out? I can't do this one in my head. It's going to be about what? Square root of 3, 3 over the square root of 3. Probably just under 2. Am I looking at this right? Is there a calculator to help me out? Just make it awkward. Pull up an Excel. 102 minus 105 divided by the square root of 144 over 50. So what, negative 1.76, right? So approximately. Well, if I were to plot this, here kind of my test statistic, which is a z value now, negative 1.76. Is that in my rejection region? No. So I failed to reject at the 1% level. Well, what about the next level, right? So I believe if we go back to that student T table, would have been up here. There we go. If I look at the 5% level, what would my critical values be? Positive, negative 1.96. Here's my rejection regions. So can I reject at the 5% level? Not quite. I'm just below that, right? Negative 1.76 is a little bit less than, if this is small, hold on. It's a little bit less than negative 1.96. But then what about the 10% level? Well, there, my critical values are negative 1.65 and positive 1.65. Now, my test statistic is in that rejection region. So sometimes we are able to say, based off the sample evidence we found, I can reject that assumed true value of 105 at the at the 10% significance level, right? I can't reject it at the 5 or 1%, right? Now those significant levels will also, I'll start talking about, they correspond to different levels of confidence. So that 10% significance level, if I'm rejecting it at that level, I'm saying I can actually reject it with a 90% confidence, right? So I'll talk a little bit more about confidence intervals, and I think that'll make sense why those two things line up. But essentially we're saying the sample evidence we found, if it is outside of our critical values, if it is in the rejection region, there was only a 10% chance that what we assumed to be true is in fact true.
What was your critical value in there?
So
I just can't see it.
these three values right here. So we'll have 2.58, 1.96, 1.65. I had the same values here, but negative. And then my test statistic I was plotting was that negative 1.76. Yep. Maybe I'll use the dot camera. I thought this was going to be much easier for you guys to see, and now I'm realizing I don't write with chalk a lot. So basically, you're going to find all three of your critical values. Once again, we didn't have to draw this out or go through all this, because once I found my test statistic, forget my chalkboard. Once I found my test statistic, which was negative 1.76, I could take my 3 critical values that we found from that student t-table. And what was the general kind of rule we said? Well, remember, these critical values, technically, I had positive and negative since it was a 2-tailed test. But the rule of thumb was, if the absolute value of our test statistic is greater than the absolute value of our critical value, then we reject. So here, I could very quickly say, okay, here's what? 1.65, 1.96, 2.58 is 1.76 greater than 1.65? Yep, so I can reject. It is not less than 1.96, so I fail to reject. It's not less than 2.58, so I would fail to reject there as well. Okay? Any questions on that? Okay. So that should take us where we at. So hopefully everyone can get this question correct. So this is where I'm saying a lot of times even, yeah, I'll have you talk to each other, work on it amongst yourselves, but sometimes we'll work through it together. And then if you're paying any ounce of attention to what we just did, you should be able to get the correct answer here, right? Just walk through it again, right? So sometimes we can reject at certain levels, but not others, okay? Any questions on this? And so hopefully you've got your answer for 2, 3. Like I said, don't worry about 1. I can get on the back end and just kind of give everybody credit for that who was here responding. Submit your quiz. So make sure you're submitting your quiz right now, because I think I had it set to be done at the end of class at 11, right? Yeah. So make sure you're going to get submitted. Yeah.
Just to clarify, Chris. So, when you have alpha equal to 0.1, right, so 10%, I guess.
Yep.
That's the value that you're using, right? Not the 0.5, since you're doing a 2-tail test.
Yeah, so that still is what you would call your significance level. It's just that now there can be evidence on the right or left side that goes against the null. And so to find your critical values, you're going to only have half of alpha in each tail. So these would be like the values you look up in the table. But you still have a total of alpha in both of your tails.
Right.
Does that make sense?
Yeah, so your confidence would be the 10, not the 0.5.
Correct. Your confidence level, your significance level is always based off alpha. And alpha is the total area in your tails. Total. If you only have 1 tail, it's the area in your tail. But if you have 2, it's the total area in your tails. Yep. All right. Any other questions before we keep moving here? So didn't get quite as far as I want, so I might hold off putting that. Well, I might alter the quiz before I post it. I'll get that kind of posted later this afternoon once I get back to my office. I might change a couple of questions because we didn't get quite as far as I'd wanted to. I may put it off until next week. Kind of give you guys a little bit more time. After class on Tuesday, we'll have covered all the material. I want to make sure you're going into that quiz and then understanding that you've covered everything. I'll still put up the practice problems though. So at least like the first 75%, you can probably start to work through and get an idea about what those quiz questions will look like. I might use those in-class quizzes next class. Might use it next Thursday. Those are going to be kind of random, but this is how we kind of institute them. You still have questions over how to get stable working on your device. I've got a limited amount of time, so I got to get a 20-minute walk through the next class. But if we don't get it solved here, stopping by my office 10 to 1 tomorrow, or early next week would be a really good solution. All right. Have a fun, safe weekend. I'll see you guys on Tuesday.